Hey everyone, and welcome to this explainer. Today we are going to strip away all those classic Hollywood sci-fi tropes. You know, the glowing red eyes, the dystopian talking robots. We're getting past all of that to figure out what artificial intelligence actually is, right under the hood. We're going to literally deconstruct the anatomy of a machine mind.
Okay, let's dive into this and start with a foundational definition. So what is artificial intelligence? It's basically the capability of computational systems to perform tasks that we usually associate with human intelligence. We're talking about things like learning, reasoning, and perception. It's not magic, guys. It is just engineering, high-level math, and computer science all coming together to build software. Software that essentially lets machines perceive their environment and maximize their chances of hitting their defined goals.
But that immediately brings up this massive, kind of mind-bending question. How do you actually build a mind from scratch? I mean, if you really stop and think about it, human cognition is just incredibly complex. Simulating that whole process, recreating human intuition, logic, and perception inside a machine is hands down the ultimate puzzle of our time. To tackle this, here's our roadmap. We'll hit defining artificial intelligence, the goals of AI, core techniques in logic, and finally wrap up with machine learning and neural networks. We're going to break this monolithic topic down into totally logical, digestible buckets. So, moving right into Section 1, defining artificial intelligence. To understand where this is all going, we really have to look at its foundational roots. And you know, the journey of AI hasn't been this perfect straight line upward. It was actually founded as a proper academic discipline way back in 1956. Over the decades, it went through these crazy cycles of massive optimism followed by just brutal periods of disappointment and lost funding. Researchers literally called these slumps AI winters. But look down at the bottom of this timeline. Things changed fast. The 2012 surge was totally driven by graphics processing units, GPUs, which finally gave us the raw hardware muscle we needed to accelerate neural networks. And this brilliantly illustrates what happened next. The 2017 transformer architecture completely revolutionized the software side. That one-two punch led directly to the 2020s explosion of generative AI for media creation that we're seeing absolutely everywhere today. All right, let's shift gears into Section 2, the goals of AI. Let's look at the distinct traits researchers are actually trying to simulate. The whole crazy idea of creating a general intelligence is actually broken down into much smaller, specific sub-problems. We're looking at things like reasoning and problem-solving, knowledge representation, planning and decision-making, learning, natural language processing, and perception, like computer vision. Think of these as the individual puzzle pieces you need to snap together to simulate a complete human mind. It's kind of like how a toddler grows, right? First they learn to see, then they learn to speak, and eventually they learn to reason. You just can't build a functioning brain all at once. You have to teach a system how to perceive the world visually and auditorily, then how to reason about it, and finally how to act on it. But here is where it gets unbelievably tricky. We run into what's called the common sense knowledge problem. This is the immense, hair-pulling difficulty of programming the vast, often nonverbal set of basic atomic facts that an average person just intuitively knows. Think about how hard it is to teach a machine basic human intuition. We just inherently know that water's wet, right? Or that if you drop a glass on a concrete driveway, it's going to shatter. We don't have to bust out a calculator for the physics. So much of what we know isn't even stored as verbal facts in our own heads. So trying to code that intuitive, everyday default common sense into a machine, it remains one of the absolute hardest ongoing challenges in the entire field. Let's move to and see how this builds into actual rational decision-making. So how does an AI agent actually make a choice when it hits a problem? Well, it typically uses this three-step utility procedure. First, it assigns a utility number to every possible situation. Basically, it's measuring how much it prefers a specific outcome. Second, it calculates the expected utility weighted by probability because, let's face it, the real world is super uncertain. And finally, step 3, it simply chooses the action with the maximum expected utility. Imagine a self-driving car trying to decide whether to slam on the brakes for a plastic bag blowing in the wind. It quickly calculates the probability that it's just trash versus, say, a solid object. It weighs the utility of keeping a smooth ride versus crashing, and then it just picks the safest mathematical action. Moving right along to Section 3, core techniques and logic. This is where we shift from the goals to the actual mathematical tools used to get there. So to make those utility decisions we just talked about, AI programs have to search for solutions, and they generally use two primary methods. First up is state space search, which searches through a massive tree of possible states to find a path to a goal.
It's kind of like mapping out 5 moves ahead in a chess game. But there's a big catch here. Exhaustive searches often run into a combinatorial explosion. Basically, the number of choices gets so astronomically large that the computer just grinds to a halt and gives up. That's why we also heavily rely on local search. This method just begins with an educated guess and then incrementally refines it using mathematical optimization. It just tweaks its parameters step by step by step until it gets as close to the optimal answer as possible.
Then we have formal logic. This is a system used for reasoning and knowledge representation. It uses propositional logic, which is all about strictly true or false statements, or predicate logic to prove conclusions from premises. For decades, this was the absolute bread and butter of AI research. It's an incredibly rigid, rule-based approach. The problem? Well, the real world is messy. It is rarely just definitively true or false. So, when dealing with vague, uncertain, or just incomplete information, these rigid logical systems can become totally intractable. In other words, mathematically impossible to solve. Because the real world is so messy, AI has to navigate it using probability and economics. Researchers rely on probabilistic methods to overcome all that uncertain or incomplete information. For instance, they use Bayesian networks for probabilistic reasoning, so the system is continually updating its beliefs as new evidence rolls in. They use Markov decision processes to evaluate how states change over time. And they even use game theory for multi-agent interactions, which helps predict how other intelligent actors are going to behave. This is exactly the math going on behind the curtain when an AI tries to beat you at a video game or tries to route you through rush hour traffic. It allows the machine to confidently operate in the gray areas of reality, making the best mathematical guess instead of getting stuck waiting for a strict true or false command. Okay, now we arrive at Section 4, Machine Learning and Neural Networks. This is really the climax of our explainer, where rigid rules give way to dynamic statistical learning. Now, what's really interesting about this slide is the massive paradigm shift it shows. This is the fundamental difference between the two primary learning styles in machine learning. First, we have supervised learning, where the training data is explicitly labeled with the expected answers. It's literally like a teacher showing the AI thousands of flashcards and explicitly saying, this is a cat and this is a dog, until it finally learns to classify them. But then there's unsupervised learning. This is when the model is handed completely unlabeled data, and it has to figure out the patterns, structures, or clusters entirely on its own. No prior human guidance whatsoever. And that brings us to the absolute powerhouse behind modern machine learning, the artificial neural network. Let's define this clearly and completely dispel the magic here. An artificial neural network is essentially an interconnected collection of nodes that loosely, and I mean very, very loosely, models the neurons in a biological brain. It's trained to recognize complex patterns in data. So no, it is not a conscious thinking brain trapped in a server rack. It is just highly advanced, biologically inspired mathematical pattern matching. So the crucial point is really understanding how this architecture actually flows. We start with an input layer, which receives the initial raw data. Next up are the hidden layers, which process that data. And by the way, if a network has 2 or more of these hidden layers, that is exactly what we mean when we say deep learning. Finally, the output layer delivers the ultimate pattern recognition. But the real secret sauce here is the weights. As data moves through the network, a mathematical weight is applied at every single node. The data only transmits to the next layer when a specific numerical threshold is crossed. Think of these weights like dials on a massive studio soundboard. Through pure trial and error, the network continually twists and adjusts millions of these dials until the final output sounds absolutely perfect. Now, network architectures vary pretty wildly depending on the job they need to do. Feed-forward neural networks are pretty straightforward. The signal passes sequentially in only one direction, straight from input to output. But recurrent neural networks, or RNNs, are super fascinating. They actually feed the output signal back into the input. This creates a sort of continuous loop, giving the system a form of short-term memory. This means the AI can process long sequences of data and actually understand things like context and long-term dependencies in a paragraph of text. Fun fact, that's exactly how your phone manages to autocomplete your sentences so accurately. To see just how incredibly fast the deep learning approach has accelerated the whole field, let's look at this timeline of natural language processing. Back in the 1990s, NLP was so computationally starved that it was restricted to tiny, strictly controlled domains we called microworlds, like a program that could literally only talk about moving virtual blocks around on a table. Fast forward to 2017, and the transformer architecture completely revolutionizes how models handle context using attention mechanisms. By 2019, GPT language models start generating highly coherent, surprisingly human-like text. And by 2023, these models were casually achieving human-level scores on the bar exam, the GRE, and the SATs. In just a handful of years, we leaped from clunky microworlds to incredibly fluent reasoning language models. It's wild. Which brings us right to our conclusion, and really the ultimate endgame of all this technology. If neural networks can theoretically learn to approximate any mathematical function, how close are we to a machine that can actually learn to be human? This brings us to artificial general intelligence, or AGI, the idea of an AI that can handle pretty much any cognitive task, at least as well as you or I could. We've clearly mastered narrow, highly specific tasks, but as we keep scaling these massive networks, that pursuit of AGI remains the most provocative, high-stakes frontier in science today. As these machines inevitably learn to think more and more like us, the real question is, how is that going to change what it means to be human? Thank you so much for joining me for this explainer, and as always, keep your curiosity sharp.